Welcome to Brain Vision.
The force exerted by the magnetic field is given by I times L cross B, and so the magnitude of force is going to be ILB times sine phi, where phi is the angle between L and B, and the direction of F is given by right hand rule being applied on the length of the direction of the flow of current and the magnetic field direction. Now, for the wire to remain at rest, the net force on the wire should be zero. That is, the force exerted on it, on the wire, by the magnetic field must have a component directed up the incline. So, like that. So, there should be a component of magnetic field along this direction. Now, to produce a force in this direction, the current on the wire must be directed left, from right to left in the figure with the problem in the textbook, or viewing the wire from its left hand end, from the left hand end, the direction should be as shown over here. So this is the image of the wire from its left hand end, and so we have a magnetic field, a component of magnetic field upwards, so that there is a component of magnetic field along the direction of incline, and force is here, and so current must be directed from left to right, so sorry, from right to left, so that should be like this. So current going from this angle, the current should be coming out of the plane of the screen. So we draw the free body diagram of uh, this for the wire. So this is the free body diagram that I have already drawn. So basically, y uh, is the direction of the incline upward, and x is perpendicular to that, and x points, positive x is downward. And since fi points here, we have components along x and y direction, and similarly for mg, which is the gravitational force. And since the net force on the wire is zero, for the wire to be at rest, we should have f summation of fy to be equal to 0, and yeah, basically that. We should also have summation of fx to be equal to 0, but as you can see, fx consists of all the forces along the positive x direction. So to counteract that, we have the normal force, the contact force from the plane of the incline. So this is going to be Fi sine theta plus mg cos theta. So these two forces minus n, because this is in the opposite direction, is equal to 0. But we basically don't need the normal force here, so we can just ignore doing this calculation. So we go with the net force along y direction to be 0, and this gives Fi cos theta, which is in positive y direction, minus mg sin theta. The minus sign is because mg sin theta points in the opposite direction to this force, and this should be equal to 0. And this gives Fi. Okay, so before doing that, let's just use the value of force, the equation of this force to be this, because force is basically the magnetic force. So we are going to use this equation times cos theta minus mg sin theta equals to 0. And since the angle between L and B, the current, direction of current and the magnetic field, as you can see here, is 90 degree. So sine phi is basically 1. So the equation reduces to this. Now we can solve this equation and we get I to be equal to mg over lb times sine theta over cos theta. And we know that sine theta over cos theta is tan theta. So I is equal to mg tan theta over L times the magnitude of magnetic field.